Let's jump straight in. If you're tired of theoretical tutorials that don't actually hold up when real traffic hits, you are in exactly the right place. Welcome to the Explainer. Today, we're stepping out of the sandbox and into the brutal, unforgiving reality of production at scale. We're going to break down how senior backend engineers intuitively know where a system is going to break before it even deploys and the exact architectural trade-offs they use to squeeze out massive performance gains.
Right off the bat, I want to hit you with a hard truth. It's something that really separates the novices from the veterans. Your value as a developer actually goes down the more code you write. I know, it sounds totally backward. Junior devs usually think their primary job is to create, but once you've survived enough production outages, you quickly realize every single line of code is a liability. It's something to maintain, something that can break, and something that adds to everyone's cognitive load. The absolute best code? It's the code that literally doesn't exist.
Think about the typical developer's contribution graph. It is essentially a tale of two mindsets. A junior developer is out there building mountain peaks of new features, maybe adding 50,000 lines of code in a single year. But a senior engineer, their graph often looks like a massive valley of deleted code. They might join a team and, in their first month, systematically wipe out 15,000 lines, kill off 3 redundant microservices, and consolidate the rest. And the result is wild. Bug reports plummet, performance spikes, and the entire system becomes infinitely easier to reason about.
So, here is our roadmap for today's explainer. 1. The production reality. 2. Taming the data layer. 3. Distributed scale and resilience. 4. Surviving production incidents. And finally, 5. The deletion paradox. We're moving fast, jumping from micro-level database tweaks all the way up to macro-level system philosophies.
All right, part 1, the production reality. We're talking about building for resilience and unpredictability. Look, in local development, the network is always fast, your database responds instantly, and data always matches your expectations. But in production, none of that is true. That brings us to the permissive parser rule. This is an absolutely vital guardrail. Senior engineers know that tight coupling between your client and server is basically a ticking time bomb. Think about it. If you use strict JSON mapping on your front end and your back-end team accidentally drops a non-critical field, boom, your entire app panics and crashes for every single user. But if you build your clients to be robust by using optional types and safe navigation, you're essentially assuming the back-end is occasionally going to have a bad day. You protect the user. That is true structural resilience.
Moving right along to part 2, taming the data layer. Let's dig into indexing trade-offs and query optimization, because your database is almost always the ultimate bottleneck.
Before you start throwing expensive hardware at a scaling problem, you absolutely have to understand mechanical sympathy, how your database actually finds information on disk. B-trees are usually your safest default, right? They only take 3 to 4 disk jumps. Hash indexes, on the other hand, are incredibly fast for exact matches, but they completely break down the second you need a range query or need to sort data. But here is the massive catch. B-trees come with a tax. Every single time you insert or update a row, the database has to update that tree. Over-indexing will literally kill your write performance. A senior engineer doesn't just blindly add indexes. They carefully analyze query patterns and balance the read speed against the write overhead.
And speaking of database bottlenecks, we have to talk about a silent killer, the infamous N+1 query problem. This is where modern ORMs completely betray you. You fetch a list of 100 users, and suddenly your code accidentally fires off a separate database query for every single user's profile. You end up with 101 queries taking maybe 800 milliseconds. Locally, you don't even notice it. But in production, the network round-trip time alone will completely drown your connection pool and bring your app to its knees. By using eager loading to batch those requests into a single query, you can get a massive 54 times performance improvement, dropping that time down to just 15 milliseconds. It's totally non-negotiable at scale.
Okay, part 3, distributed scale and resilience. Let's see what happens when one database just isn't enough and we have to scale out horizontally with asynchronous messaging. When you move to a distributed architecture, physics always wins. Take Kafka, for example. You literally have to make a choice between low latency and high throughput. You simply cannot have both perfectly. If you're building a real-time trading platform where every millisecond matters, you have to slash your batch size and set your linger time to near 0, probably using a super fast compression like LZ4. But if you're building a massive analytics pipeline where sheer volume is all that matters, you tell the producer to hold up. You increase that linger time to maybe 100 milliseconds, pack a massive 128 kilobyte batch, and crush it with ZSDD compression. It is a highly deliberate, engineered trade-off.
Now here is an absolute nightmare for any senior engineer.
Failing at asynchronous resilience. You have to avoid these idempotency red flags at all costs. In a distributed system, network timeouts are basically a guarantee. A client will retry a request. If that request is processing a payment and you haven't built proper idempotency keys, congratulations, you just charged a customer twice. The biggest trap here is confusing idempotency with exactly once delivery. Exactly once is incredibly hard. What you actually need is a system that can safely process the exact same message multiple times without changing the final state, and definitely without just silently dropping errors to make the dashboard look green.
Let's head into Part 4, Surviving Production Incidents. These are the debugging methodologies for Day 2 operations, when things inevitably go wrong.
This is for those moments when your dashboards are flat out lying to you. Imagine your APM shows 100% success rate, CPU is fine, but users are screaming that the search bar is broken. Why? Well, maybe a bad feature flag introduced a malformed SQL query. The application gracefully handled the database error and returned an empty JSON array with a 200 OK status. So the metrics said everything was perfect, but the actual payload was completely useless. To find that logical null pointer, you need this 6-step semantic debugging process. You have to step outside the metrics, hit the API directly with curl, and manually verify the raw output. Senior engineers don't just trust green lights, they hunt for the semantic mismatches where the business logic silently failed.
And to ensure you're not missing those critical golden signals, you need the USS method, tracking utilization, saturation, and errors. If you just monitor CPU percentage, you are flying completely blind. You might see CPU at 80% and think you have plenty of headroom. But if you actually look at saturation, like the CPU run queue length, you might see hundreds of threads desperately waiting in line for execution time. Measuring utilization without measuring the waiting line is a guaranteed recipe for a cascading outage.
Then there's the scale and trade-off trap. Imagine an exploding list in Java, like an unbounded cache that just keeps growing until it finally triggers an out-of-memory error. By the time the app crashes, all the evidence is totally wiped out. But by deliberately paying a tiny 1 to 2% CPU penalty to run connection leak detection continuously in production, you basically buy an insurance policy. It gives you the ability to instantly pinpoint the exact line of code causing the leak the very second it starts happening. Sacrificing a little bit of compute overhead to prevent a multi-hour outage? Absolutely worth the trade-off.
Finally, Part 5, the deletion paradox. This is where we see that simplicity always beats sophistication.
We've talked a lot today about complex tools and fine-tuning, but the ultimate optimization is entirely different. It's getting rid of things. Every unused feature, every redundant parameter, every premature optimization, it all adds to your team's cognitive load. Think about that super clever abstraction someone built to handle a theoretical edge case. Someone else is going to spend 3 days just trying to understand it next year. That caching layer you added for a table that updates once a month, that's just another system that can fail. Replacing thousands of lines of code with a blank void actively destroys false complexity, reduces bugs, and makes the whole system drastically faster.
So I want to leave you with a provocative thought to challenge your daily workflow. The next time you go to build a feature, add a dependency, or architect a new microservice, pause and ask yourself, what can I delete instead? The path to mastering backend architecture isn't paved with more code. It's carved out by relentless strategic deletion. Thanks for joining me on this explainer. Now I challenge you. Go pull up your codebase right now and find something to delete.